So I've started having a look at these Zen 8Ks already, and this one I just gave a quick go at because it was a very basic repair that I've covered a million times on my channel. It only had a power supply failure, the output section's just fine. So all this needed was a whole new set of drive transistors in the middle here. So these are BD139 and B772 drive transistors, NPN and PNP in the correct locations. And then it just needed some new some power supply MOSFETs, 064Ns, and we need one per bank. So we've got two on each transformer, push pull, etc, etc. Now interestingly, usually on idle the amplifiers don't draw a huge amount of current, and the power supply FETs all stay pretty cold. So on this amplifier, the power supply waves look beautiful. It was a basic repair, all new drivers. The TL494 is good. The drive waves on the power supply look really nice. The output section activates and builds its Class D PWM beautifully as well. Looks all good, and the amplifier stays running happily. However, it draws quite a bit of current, and the power supply FETs get quite hot on idle. They all heat to exactly the same amount, so they're all heating in a uniform fashion, suggesting that whatever's causing them to get hot is either a uniform drive issue, so they're all being driven slightly incorrectly, causing them to all heat up to the same amount, or the output section is drawing current from the power supply, causing them all to heat up as the current is shared between all of these FETs. So if I power it up now, you'll start to see what I mean here. So this is the power supply drive waves, and as you can see, the push-pull looks really nice. It's fine, and we've got a bit of noise on there due to the power supply. And the amplifier is on 9.2 volts. It draws 8.9 amps. That is really high. That's unusually high, and as a result of that, the MOSFETs do draw a they do get pretty warm, and I'll show you on the thermal imager just now. So yeah, as you can see here, they're all reaching, after just a few seconds of operation, they reach sort of 28, 30 degrees, 32 degrees, and they continue to climb in this fashion up to sort of about 40 degrees. Like I said, it could be that the output section is drawing current from them, and there might be an issue there, or it could just be that they require all of the power supply FETs in the board in order to operate correctly. But I'm still concerned about this high current draw, this 8.95 amps of current draw on idle at only 9.2 volts of input voltage. So what I'm going to do is I'm actually going to put this one to one side for the moment. We're going to go and grab the other Zen 8.5K, which has a perfectly functional power supply. We're going to remove all of them. We're going to remove the output MOSFETs and the drive board from the other Zen 8K to pretty much disable the output section and see if it draws the same current as this one does from the power supply. Alternatively, if you only had one of these amplifiers and you were trying to work out what was causing that excessive current draw, you could remove all of the rectifiers here. So here and here, just pull them out of the board, and that isolates the power supply from the output section. So if then, after removing the rectifiers, the amplifier still draws a lot of current and the power supply FETs still get hot, then you know that it is most likely a drive fault that is causing those to heat up and draw current. However, if with the rectifiers removed from the board, the power supply comes on and draws very little current and these all stay cool, then you know it's the output section which is drawing current from the power supply, causing them to heat up. I decided it was probably quicker and better to show you guys, just to remove all the rectifiers on this one and see what happens, whether it still draws current or not. So all the rectifiers are now out. Let's power up and see what the current meter says. There we go. So yeah, that is I've got the probe on the rectifier output there. The amplifier is now only drawing 3.5 amps, which actually is quite a lot for just an idle power supply, to be perfectly honest. Like usually they draw less than an amp. So yeah, I'm wondering whether it's actually something in the power supply. So if we assume that the output section, when coupled with the idle of a normal power supply being about 1 amp, and the output section causing the amplifier to draw, say, 4 or 5 amps, that would usually result in about a 6 amp idle. And this is running at like 9 amps idle. And so we currently have almost a 4 amp idle coupled with a 5 amp idle, which gives us 9. So I think the issue might be in the power supply, not the output section drawing current. So let's turn the thermal imaging camera on again and run this, see what we get. Yeah, so the power supplies FETs are still heating up even with the rectifiers out of the board. So that now confirms that whatever it's not perfectly happy about is just down to the power supply itself. The fact that they are all heating up to the same amount means that it's a drive thing that's causing that, because the output rectifiers here, they're not linked between banks. So if there was an issue on one drive or one of the transformers or something, then it would only be that bank of FETs that got warm. However, because it is all of them, that suggests that something on the drive is not quite right. It could be that the amplifier needs all of the power supply FETs to be present in order to correctly deal with the gate capacitance and the ringing circuit and the snubber circuit. But that's very uncommon. I've not seen that happen before. So I'm going to look a little bit deeper into this. It may be a case of, just because of convenience, getting the other Xenon 8K out, which has a fully functional power supply, removing the rectifiers on that one, and comparing the shape of the drive waves, the frequency, and other things to see what the hell is going on here. What I've done is just to confirm that actually they don't heat up with all 6, and it's not to do with ringing, it's just to do with gate capacitance. I've removed all the other ones just to run this one independently, just to see how much current one of these draws, and to see whether they all get hot or not. Okay, so that is drawing 1.13 amps. That's quite a lot for a single one of these. And if we look at the output of these here, you can see that there's a lot of ringing. There's a lot of ringing there. Yes, I mean, they're reaching like 32 degrees, which isn't like horrific. They should be dead stone cold. They shouldn't be any different to the ambient temperature around. So the fact that there is a bit of heat on there, and I think they're climbing slowly, suggests that there is maybe still a problem somewhere with the drive circuit, perhaps. Yeah, they're warmer than they should be. It should be a dead stone cold thing on here, especially without any rectifiers. So I think what I'm going to be looking to do is, rather than spend hours digging around for a strange drive circuit fault, which doesn't really make a great deal of sense, seeing as we've got all new drivers in, I'm going to take the other Xenon 8K out and see what that one's doing, and see if I can make comparisons between the two, because the other Xenon 8K has a perfect power supply. The power supply didn't blow, so it is completely stock. So we can use that to make comparisons to find out quickly what's wrong with this one. Right, so this is the amp we were just working on, and this is the second one that has a perfectly untouched power supply from factory. We removed the rectifiers in this one as well, and we still have the same ringing on the output wave of the MOSFETs and the power supply. And we have high current draw. So it looks like this is just a feature of these boards. It's very badly optimized power supply. I'm not a fan of that whatsoever. That's fucking bollocks, that is. So that's actually a good thing. That means that we haven't got to piss around with the power supply on the other board. That's straight up fine, that's repaired. So actually, that amplifier there, that's ready to go, that's fixed. That's fucking, all it needs now is it just needs a whole bank of new power supply FETs, easy peasy. Back in the case, good to go. This one, however, is going to be fun because we're going to start looking at the output section now. Cool, so rectifiers are back in. So this is the one with the dead output section that we can start working on. Doing a quick visual inspection here, my man. So by the looks of things, the only visual signs of damage on the output section is this stuff over here. So this is 4 amplifiers in parallel. We have 4 output inductors, and we have 4 drive ICs. This shows that there are 4 separate amplifiers on this board that are paralleled after the inductors to drive a 1 ohm load. So this amplifier on its own, 4 ohm, 4 ohm, 4 ohm, 4 ohm, then you go 4, 2, 1.3, 1, that gives you your 1 ohm rated stable fucking bollocks. So by the looks of things, the only visible damage that we have is to this amplifier here. That doesn't, however, mean that none of the others are damaged as well. Output FETs are much less likely to show visible signs of damage when they blow than power supply FETs. But this has gone down in quite a heavy way. This is full high voltage rail, absolutely like shorted straight in and instantly through these FETs. So the first thing, because these are obviously dead, the first thing that we're going to do is, or first thing we're going to get Brad to do, is just to snap these off, because it's just quick. So just literally just wiggle them around, or cut them off if you've got cutters. So get rid of the ones that are visibly damaged in the same parallel bank. So if you have one FET that's in a parallel bank with another FET that's dead, the other one is going to be dead, or you can't use it anyway, so you might as well just snap all these off. So we're going to go up to we've got 1, 2, 3, 1, 2, 3. So each amplifier, each one of these sections of amplifier runs 3 high side FETs and 3 low side FETs. So we're going to get rid of both high and low on this amplifier here, this one. Yeah, so on this pad you can see how much of a flipping arc there was, or how much how much energy was in the spark. It's completely evaporated, disintegrated like a whole chunk of this board trace here. So we're just going to clean this up, and we're going to get a better view of what that looks like. Got some 99% isopropyl alcohol. Very important that it's very, very high concentration alcohol content. Any impurities in that are conductive, so it's not ideal for working with electronics. You've got to have the purest alcohol content you can find. It's a nice pattern on that trace there. So that's a big old arc that is. Right, so it's good to actually stop and just have a quick look at this stuff and just take it in with your eyes. So here we have this great big arc here, this pattern. Right next to this, there is a trace here that has the insulation lifted off the trace. It's been burnt off or whatever, so you can expose the copper. So it's possible that high voltage may have ended up finding its way onto this trace. Now this trace, if you follow it, comes from the power supply section, and it goes to all the way up the board here. So you follow it along the side of the board, and it ends up going into the low voltage regulators, which are the things that give power to the drive ICs, op amps in the preamp section, etc. So if high voltage did spark out on this trace, it's possible that it may have killed some of these voltage regulators. So because of that visual inspection, before we try and power the board up at all, we're going to flip the board over, just make sure these aren't shorted out. Cool, so now we've removed the obviously visible dead FETs, we're going to go ahead and check for shorts on the other banks that didn't show any visual signs. So take a multimeter and whack it to diode beep setting, and we're going to probe between all 3 legs, so 1 and 3 and 2 and 3 of the remainder of them. It's a cool idea as well to just check for shorts on the ones you've removed. Sometimes the driver itself will be so badly damaged that it will just create a short between gate and source. Or gate and drain. No, maybe not gate and drain. Usually gate and source. Go ahead, and we're going to run along and check the other FETs here. Yeah, this amplifier probably seems alright. And go over to the other side of the board. So in this case then, it seems that we did just lose 1/4 of this amplifier. Now, the drive circuit for this may very well be damaged. It's you can't really tell just using a multimeter like that. One of the best ways to tell whether a drive circuit is completely fucked or not is to apply a tiny bit of power to the amplifier to build the voltage in the rail caps to about ±5 volts. Just a tiny touch of the remote to build the rails enough, and that shows you if there's any leakage going on the drivers. Now these amplifiers, the IRS21844S chip, it drives the FET directly, and these are very, very delicate chips. So if you have this scenario that happened here, it looks like quite a dramatic explosion here, most of the time it kills the drive IC. Not always, but most of the time it does. And you can't always see that with the multimeter. So what we're going to do now is I'm going to get Brad to turn on the power supply. I just tap the remote and just let the voltage build to about sort of 5 or 10 volts. Give it probably like hold it for a couple of seconds. So we've got however many volts on that now. If we click the measure button, got 17 volts on the high side, and if we probe the low side gate, which is number 1, that's the source. Yeah, that's the same anyway. So we should have, yeah, that's looking about right. So to check whether the driver's all right or not, we check the low side and the high side. So the high side, which are these ones, should have nothing on pin 1, which is the gate. That's correct. Should have high voltage on pin 2, which is the positive rail. That's correct. And on pin number 3, it should have nothing. Let go and do it again. That's -800 millivolts. It's probably fine. It's just difference in ground. So check the low side now. The low side should have negative on number 1. Okay, Okay, let go. And number 2 should have nothing. And number 3 should have negative. Go back to the number 1. So that pad isn't showing anything. So we've pulsed the remote a bit longer now to give us more voltage. So if you probe the high side drain, the middle one of that, so yeah, we've got about 36 volts on that now. If you go ahead and probe the gate of that, that's dropping down to like negative 2 volts. That's not right. It should be dead on 0. And if we probe the low side gate, it's number 1, we got minus 16 volts, which is no good. If you probe the source of that, the third pin, the third one, right side, yep, we've got minus 14. So there's all sorts of voltages where there shouldn't be, which isn't right. I'm going to bank and say that those voltages probably aren't present on the good stuff. Let's have a quick look. So this is going to be the low side. Yeah, so this is looking more correct. So on number 1, we do have the correct negative rail, and pretty much nothing on the middle. On the high side, we should have pretty much nothing, and then positive on the middle, which is that's looking about right. So yeah, looks like we have a problem with the drive IC, which is the most common thing to fail when it goes down in this way. So the way to work out which chip is related to this bank of outputs here is we take our multimeter and we measure from this back side of the gate resistor, and then we put the other multimeter probe on the pins going into the driver board, and then whichever one beeps, we then follow it to the chip. Or we can just measure the chip directly. Just run our multimeter probe across the legs of each chip, and whichever chip it holds the beep on, that's the chip that is driving this set of outputs. But before we do that, let's wait for the rail voltage to sink back down to 0, otherwise we'll short out some other stuff with the multimeter probe.
Yeah, doesn't matter.
So what we're going to do is going to put the multimeter probe on the input of the gate resistor. So for example, yeah, so that one there, that's fine. Wait for this to focus. So yeah, that one's fine there. Now with the other probe, we're going to run it along the pins, that's it, run it along the pins of the chips, and whichever one it holds a beep on, that's the chip that's driving that set. Oh, wait. Yeah, looks like that, maybe that one. Yep, yeah. So it's that second chip in there, that one. So in order to change that chip, we're going to be wanting to remove the driver board from the amplifier, and then use the hot air station to change the chip. So yeah, this bit's always fun. Driver board removal. For people that haven't removed the driver board before, it's very, very easy to lift traces, pull veers. You're trying to whack it out super quick. So the method that I go for with the driver board removal is, first of all, start by just simply sucking the solder from each of the pins like that. So you go along and get most of the solder out of each pin. You don't have to get all of it out just yet. Just go along and get as most of the solder out of each of the holes as you can. Once you've done all of the pins, some of them, it will have successfully removed all the solder, and if you give the driver board a wobble from underneath, so if you take the top of the driver board and you wobble it around, you'll visually see the pins wobble in the holes. So those are the ones that are free. So what you do is you keep wobbling the driver board and sucking the rest of the solder from the remaining holes that aren't wobbling, and then after each suck, give the board another wobble to see if that leg is now free, and you keep doing that until eventually you find that all the legs are free and the driver board then becomes really loose because it's all just free. Then you can just pull it out and it will literally drop out the board. So you can see how most of those pins are wobbly there. Give it another wobble, Brad. Yeah, they all look wobbly. They all look wobbly. And they're all getting a good old wobble on. That one there, is that? They're all looking nice and wobbly now. So they're wobbly, so they're free, but there may be like there'll be tiny little sort of like serrated bits of the legs and the holes and stuff like that, so it won't just fall out. So what you have to do is you have to sort of give it a fair wiggle, and you don't have to be too gentle with it. So you have to like push it back and forth a fair bit to sort of, the solder will be soft, so you push it back and forth to like get rid of those jagged edges to the hole and to the legs, and then just give it a wiggle and pull it out. Don't pull too hard because you can still pull a veer if there is like a sharp tooth that's on the veer of solder, but give it enough wiggling and the solder will flatten itself out against the veer, and then it should come out relatively easy. But this is proving that I think these use really thin legs, so it isn't the easiest thing, but there you go, that's fine. And let's have a look at the legs. Oh yeah. Oh yeah. Oh, that gets me going, that does. Look at that, fucking beautiful. Not a single hint of veer or anything. Absolutely dead set clean. Nice. Right, so the driver board is out and we have one chip that's dead that we need to change. However, these are IRS 21844S drive ICs. I only have with me the FAN 7393 drive ICs. You can't mix and match. You can't use the FAN chip with the IRS chip. So we either need to find another IRS chip from another amplifier that lists laying around at Brad's place, or we need to change all four of them for the FAN chip. Now, interestingly, I've been using the FAN 7393 chip on a whole range of amplifiers that you've seen on my live streams. It was originally recommended by H1 Nicholas on the live chat, and they are a really good chip. However, they do have a different characteristic in regards to turn on delay. So the IRS chips, they have a longer turn on delay than the FAN chips. As a result, in some amplifiers, the FAN chips activate too quickly. They activate before the PWM generation circuit in the middle of these driver boards has actually got the correct 5 and -5 volts on the op amps here, and the FAN chips activate before these do. So it's kind of similar to how if you have a stereo system, it's a bit it's almost like turning the power amp on first and then turning on the preamp. You end up getting a pop through the speakers when you turn the preamp on afterwards. So it's the same case here. By turning the drive IC on first and then having the PWM chips activate, a pop goes through the drive line and it ends up turning all the FETs on for a brief instance. This blows the FETs in many cases or damages them. So that is not a good thing to happen. Some boards are compatible with the FAN chip. Some of them build the 5 volt and -5 volt quick enough so it doesn't cause a pop, and the FAN chips actually turn on after this does. But in many amplifiers that I've seen, actually that's not the case, and running the FAN chips causes problems. So what we're going to do now, just to show Brad give some experience to see this issue in action, what we're doing is, because this board still has FETs in it, we can't, in order to check whether the FAN chips are going to be compatible, we need to not have the FETs running. So rather than removing all the FETs, we can lift one of the legs of the gate resistors, which prevents the drive wave from getting to the FETs, therefore preventing them running. That's almost like the FETs aren't in the board. And once we've lifted one leg of the gate resistors, we can power the amplifier up and we can have a look at how the drive builds when these chips activate and see whether the FAN chips are going to be compatible in this board or not. So as you can see there, the gate resistors, we have the backs lifted, and it's very important that you don't actually just lift the leg of the FET, because you need the pull down resistor there present to pull down any static or residual voltage that finds its way onto the MOSFET gate. If you have the MOSFETs active and the gate is just floating in the air, then the MOSFET will eventually turn on just from static charge that builds up on the gate. It requires very little charge for the FET to turn on. I've had that before where I did this on an amplifier that didn't have pull down resistors, and yeah, a few seconds of operation and one of the FETs just turned on and shorted out. So very important to leave the pull down resistors in and the FET legs in and just pull the gate resistor one side up. So now what we can do is we can turn the amplifier on and we can run the driver board without risk of it actually damaging any of the FETs. So yeah, taking these chips off is pretty easy, to be honest. What you do is you just use the hot air gun, get it out to about 390, 400 degrees, not too much pressure on the hot air. You just want it just enough so that it reaches the chip. So do circles around the legs, and then when they're all melted, you'll see that the chip just pulls off the board. So if you hold the board up a little bit with the tweezers, then gravity will do its job. When the legs are all melted, the board will fall back down to the table, leaving the chip in your hand and the tweezers. Yeah, once all the chips are off, you just want to go ahead and refresh the solder on these pads, make it nice fresh solder, so when the chips go on, the new chips go on, it makes a good contact, nice and solid. So putting the new chip on, you want to reverse the process. So I want to heat up the pads first, get them nice and wet, and then what I do is I hold the chip over them there to heat the chip legs up as well a little bit, then push it onto some of the pads. Now they don't all need to make a contact at this point, just enough of them, like 1 or 2 of them need to make a contact so that the chip then gets stuck there. So you remove the heat, hold it there till they go solid again, so it's in the right position, and then let go. That's it. So now you can probably then put pressure on the top of the chip and then cook up the both sides of the legs again once more, get them all melted, and putting a fair bit of pressure on the chip from the tweezers. That pushes the legs down onto the pads, gets them all immersed under the solder, and then wait for it to set again, and then it should be jobs are good 'un. Right, so we're at the stage now where there's 4 brand new FAN chips on the driver board. We're just going to slide this in here like so. Now, when you're testing this for drive waves without the FETs connected, you don't need to resolder the driver board in, especially if you're going to be taking it in and out to make changes. It just damages the vias unnecessarily. So with the driver board not powering any FETs, you can put it back in the holes and apply a little pressure to the board, forward or back, but usually forward is better. And that makes contact on all the pins to the vias, which activates all the different elements of the driver board. And by doing that and powering the board up, we can read the drive waves on each of the low side drive pads. It'll only show drive waves on the low side FET pads. The high side requires the feedback from the low side to oscillate, so you will see nothing on the high side gate drive. You only see square waves on the low side. Now, because this is a self-oscillating amplifier, in the driver board builds the frequency based on the FET's feedback. So without any FETs in there, it gets confused as to what frequency to build. So therefore, the frequency is much slower than usual. Normally, you want your scope set to about 2 US time divide, but without any FETs in, we're going to slam it up at about 800 US, which is about right for looking at the drive waves. Maybe 400 just to zoom in a little bit. And you still want it on 50 volts divide because we're looking at the negative rail voltage which the drive wave rides along. So if I put some pressure on the driver board here, we're going to probe the low side gate hole here that the gate resistor usually sits in. Obviously it's lifted. And on the scope screen here, we'll see the negative rail voltage start to build. Let's turn the power supply on and see if there are square waves there or not. So let's hit it. Sweet, so there we go. Let's do that again and hold it on there. That's what we want to see. So that means that the chip is working correctly. It is attempting to drive the MOSFETs and build a wave. So what we're going to do now is we're going to go ahead and make sure that that is present on all of these banks. We do that off camera, it takes a while. Make sure it's present on all 4 of these low side drive banks. So just to check this one. There we go, it should be the same on all of them. Provided it is the same on all of them, then you're pretty much ready to go ahead and connect the FETs. However, because we're using the FAN chips, there is something that I want to check. What I said earlier about how they can activate too quick, we're going to go ahead and check now. This is only viewable, so if we put it, stick the probe back in this gate location here, and you leave it there, you can let go of it, just like whack it in there. Now, what happens is, I said that there was a pop or a bump that occurs through the low side drive path, and this only happens when the capacitors, the rail caps, have charge in them already, like at the moment. You have the negative rail sitting there. So what I'm going to go ahead and do is touch the remote again to build that wave, let go of the remote and touch it again. And the wave should appear as the first thing on the screen. If you get a little bump first, then that is not right. It means that the FETs are all being turned on at the same time. Sometimes it's hard to see with the scope turned onto such a fast divide. So we're going to slow the scope right down. So what we want is, you want the scope to kind of be doing this almost like a hospital heart rate monitor kind of thing here. Going to go one slower again, which is 400 milliseconds. And what we're looking for on the scope here is, you'll see the drive wave appears like a bit of noise, and you want the bit of noise to appear as the first thing on the line. If there's a little bump before it, then it's no good. So this is actually perfect. I'm going to go off and on again. You see how the drive wave is perfect? It's the first thing on the line. There's no like bump, or there's no like sharp spike before the wave builds. The wave builds cleanly and is the first thing on the line. If these chips weren't compatible with this board, what you'd see is a kind of jump up first, then back to a line again, and then the wave build, so which would not be good. I'm just going to go a little bit faster to try and show this, just to make sure, for absolute sure, a little bit faster. So you can see there that the wave is the absolute first thing to build. There's no like spikes or anything before the drive starts. So that means that the FAN chips in this case are fully compatible with this board, which is good for us, means a little bit less work. So the drive board's soldered back in, and we are just soldering 6 new FETs into this location here that died before. We've actually, because we don't have any 24N50s, but just for the purpose of seeing if it works, and I mean this will probably be fine anyway, we actually have another 8.5K Xenon. It's the other one with the dual output section rather than the quad. That's using 24N50s as well. They're a slightly different batch. However, we have used the transistor tester to check their specs, and the VT and RDS is pretty much identical to the ones that this amplifier uses originally. So, and especially since these are all being run in a separate amplifier bank than the others, having even mildly different specs isn't going to pose too much of a problem. So the fact that these are identical should mean that this is going to be happy days. Right, so now we're at the scary part where we've pretty much done all the repairs that we can see that need doing. Drive board works fine as shown by the drive waves. Fitted the FETs and checked those with a multimeter between the gate and the source. Made sure that the diode setting numbers, the readings, are identical between the batch we just replaced and the ones that survived, which they were. Perfect. So what we're going to do, in order to power this amplifier up, first we want to probe the right things so that we get an idea of what's going on with the amplifier, and we can turn it off instantly if we need to, if there's a problem. So the first thing that we want to probe is we want to probe the output of the low side. So the low side gate is the one that activates first, and it builds a square wave on the drain on pin number 2. So we want to probe pin number 2. We want to probe the output of the low side, which is the drain. So I think this was low side in the middle, wasn't it? Yeah. Is that low side and that was high side? Yeah. Yeah. So that will build a square wave as soon as the drive circuit activates. But in order to watch the amplifier slowly come on, and in order to monitor the rail voltage inside the main capacitors, we want to see the rail voltage rise just so that we know where the amplifier is at in its power up stage. So with the second probe on the multimeter, on the oscilloscope, sorry, we want to probe the high side drain, which is going to have the high voltage rail on it, the high side rail. There we go. So on the screen here we set both of the probes to 50 volts divide, which should be about right for this amplifier at this 9 volts of input. We want to turn the time divide to quite a fast refresh to US, should be about right for the output section switch. So we're going to go ahead and turn the power supply on now. Make sure it's sitting down nice and low, probably 9.8 volts, probably about right. Maybe knock that down a touch on the fine. That's already down there. Yeah, so just knock that down just a little touch. Just a lower is safer as long as it's all activating. So yeah, now comes the part where we hit the remote. So what I want to do first is just hold the remote on for about a second, just to let the high voltage rail build to sort of like 10-20 volts or so. That's about right. Just want to make sure the yellow one doesn't move. The yellow one is the low side drain. That shouldn't move. So whew, when you're ready, we're going to press the remote and hold it on fully, and we either see square waves or we see an explosion. We have square waves and off. So the first power up, we just want to let the output section switch for like a couple of seconds. If anything on the output section isn't happy, a couple of seconds of switch like that will either make it explode or it'll make it heat up. So actually it probably should have been better idea to have the thermal imaging camera running at all times when we turn it on first time. Want to monitor the temperature of these FETs. If anything's not happy, the output section heats up really fast. So just going to make sure that couple of seconds of output switching didn't heat up any FETs. On the bank that we repaired, that's looking very cold. Don't see any heating on those at all at the moment. And just check the ones that survived. They should be fine since they survived. Alright, sweet. So what we're going to do now is hold the remote on for longer, and just going to keep our thermal imager here and monitor the temperature of these FETs. Nice, that's a good looking drive wave there. So yeah, we're holding it on. We're still on 9.2 volts, so pretty low rails. Yeah, looks pretty sweet to me. Looks pretty nice. None of the FETs over here are heating up. Yeah, bang on. So the red mark you're seeing on the thermal imager, that's that pull down resistor, that great big white one. That's all right. Yeah, okay, release the remote. Happy days. So yeah, based on like assuming the 14 volt test goes all right, this is a successful repair. But so this could be the point where we finish this off and, you know, put this back in the case and whatnot. However, what I was saying earlier about the power supply, I don't like that. It runs really, really hot. Power supplies shouldn't run hot on idle on the FETs. So I think that there is a design flaw with the gate resistor value. So what we're going to go ahead and do now is we're going to put this amp to one side once the rail voltage sinks down. We're going to take the one we were working on earlier that has most of the power supply removed and the rectifiers removed, and we're going to mess around with the gate resistor value and see if we can get this power supply FETs running cooler. If we find a better gate resistor value, then we're going to apply the new resistor value to this board and to this board. And if that makes the amplifier run more efficiently, less idle current drain, then we should be able to perform the 14 volt test on this because there'll be less current demand. So let's see what we can do.